It's recording now, yes?
دكتور.
It's recording. طيب. We will now start with or continue with chapter 6, lecture 2, with work and energy. And today we will be doing kinetic energy. Uh, kinetic energy, we call it طاقة الحركة, which is an energy that an object acquires or possesses because it has speed, it's moving. And we define it like the following, that K, which we call kinetic energy, we represent it as K, capital K, equals to half times the mass of the object times V squared. So K equals to half M V squared. So clearly, if the speed or velocity of the object equals to 0, then the kinetic energy is 0. Otherwise, it's greater than 0. Any object that has velocity has kinetic energy greater than 0. The only time where the object has 0 kinetic energy is when it is where? At rest. So, in other words, kinetic energy is always greater or equal to 0. Now, we will do what we call the work kinetic energy theorem, which deals with the following question. You might ask yourselves, where does the work done on an object go? Yani a force does work on an object. What happens to that work? Is it changed into energy? And if it is changed into energy, to what energy is it changed into? That's what we will be doing now. And I have taken this example, which shows a car where a resultant force F net acts on it in the positive x direction. That car makes a displacement d under the effect of that force. Okay, and since F and d are in the same direction, the work done by this force is positive. Yes, and remember from last lecture we said that if the net work done on an object is positive, what happens to its speed? If the net work is positive done on an object, what happens?
Increase.
Yes, the speed increases, exactly. Okay, so a work was done on the object. That work is positive because F net and D are in the same directions, or they are in the same direction. So the velocity increased, or the speed in this direction increased from V1 into V2. I can call it V initial and V final. I want to relate the work done on this object to the change in its kinetic energy. Let's see how we can do that. First of all, calculate the work done by this net force. And as you all know, this work equals to the value of the net force, F net, multiplied by the magnitude of the displacement, multiplied by cosine the angle between them, which is 0, since they are in the same direction. And therefore, the work done by this force equals to F net multiplied by D. Why? Because cosine 0 is 1. Fine. Now we will use what we learned in chapter 2, which is one of the 5 equations of motion, which says that the final velocity squared minus the initial velocity squared equals to 2 multiplied by the acceleration multiplied by the magnitude of the displacement. Done. This is equation number 2, if you remember from the equations of motion. If you multiply this equation by half m, okay, you get half m squared minus half mv initial squared equals half m multiplied by 2 times a times d. The 2 cancel out, and we end up with ma times d. Now remind me, this ma, what does it equal to? Mass times acceleration. From Newton's second law. Yes, F net, exactly. So this ma, the 2 cancel out together, this 2 cancels out with this 2. So you get ma, which is F net, multiplied by what? By d. So the net work done on the car equals to F net times d, and that is what I call W net, which is the total work done on the car. And what does it equal to? It equals to half mv final squared. Remember, half mv squared is the kinetic energy. And since we have half mv final squared, this is the final kinetic energy. Minus half mv initial squared, it should be what? Initial kinetic energy. Therefore, now we have found a relation between the change in the kinetic energy and the work done. And anytime you have something final minus something initial, what do we call it? We call it delta, change. Change always means final minus initial. But change of what? Change of kinetic energy. Therefore, we have delta K, which is the change in the kinetic energy, equals to the net work done on the object. So you see that work has been converted into what? Into kinetic energy. Okay. So the work kinetic energy theorem states the following, which is the net work done on an object, which we call W net, equals to what? Equals to the change in its kinetic energy. And remember, delta K means K final minus K initial. Yani final kinetic energy minus initial kinetic energy. Now remember, in the last lecture, we said the following. If the net work done on an object is positive, what happens to its speed? إذا كان الشغل الكلي المبذول موجب، شو بصير بالسرعة؟ Increases. Let's see, can we get this from, well done. Can we get this from this formula? If this is positive, if W net is positive, this means that V final is greater than what? V initial. This is the only way to get this to be positive. This means if this is positive, this means that V final is greater than V initial. W net is greater than 0, which is positive. This means that V final is greater than the V initial. معناها final speed is greater than initial speed. Therefore, the object what? Accelerates. While if W net is less than 0, what does it mean? It means that V final is less than V initial, مظبوط. معناته the speed has decreased, which means that the object is what? Is decelerating. طيب, what happens when W net equals to 0? What does it mean? If this is
Constant
0,
speed.
exactly, it means that V final equals to what? V initial. Therefore, the speed is constant. And this is what we said what? Last lecture. Now, I have just formulated this more mathematically into this relation, which is W net equals to delta K. Okay? For always, then always the net work, if the net work done on an object is positive, if the net work done on an object is positive, this means that the speed of the object increases. If it is negative, the speed decreases. If it is 0, the speed remains the same. And this is the work kinetic energy theorem. W net equals to the change in delta K. The total work done on an object equals to its kinetic energy. What is so beautiful about this theorem is that all the questions we did in chapter 2 can be solved using this formula, except one type of problem which asks for time. يعني كل المسائل اللي في المعادلات الحركة تنحل على هذا القانون باستثناء واحد إذا كان بطلب زمن, because this does not have time. Okay, so let's see how we can use this to solve some problems that we dealt with in chapter 2, اللي هي motion in one dimension and two dimensions. Let's take this example. This is the first example that we considered. This is the third example that we considered when we did one-dimensional motion. An object of mass m is projected vertically upwards. يعني قذفناه عموديا لوين؟ إلى الأعلى. From the Earth's surface, من سطح الأرض, with an initial speed of 20 meters per second. So it's thrown upwards with a speed of 20 meters per second in the upwards direction. First requirement is find its maximum height. Now, all of you must be able to do this question using the equations of motion, which is you take an origin and you take an upwards, for example, as positive, and you use the equations of motion. Right. Is there an alternative way of doing this question using the work kinetic energy theorem? Absolutely. Yes, you can do it. How can we do this? Remember, W net, which is the net work done on the object, equals to delta K. Tell me now, what is the only force acting on this object as it moves?
Gravity.
Gravity. مظبوط. إذا هذا free fall, you see? Free fall. Only the force that acts on the object is the weight, downwards. Right. Then the net work done is that done by what? By mg. So W net must be equal to delta K, which equals to half m. I've taken half m as a common factor, into V final squared minus V initial squared. Right. What does W net equal to? Equals to mg, which is the magnitude of the force, multiplied by the distance it has moved, which is y max, okay, multiplied by cosine 180. And the reason is cosine 180, the angle between the displacement, which is upwards, and the force doing the work, which is mg downwards, is 180 degrees. So we get masses cancel out. You see, you did not need the masses at all. You get minus g y max equals to minus 200, and therefore y max equals 20 meters. This is exactly the same number that we got when we used the equations of motion. So you can use the work kinetic energy theorem to do this type of questions. Let's have another thing. Another question on the same situation. Find the speed of the object when it is at a height of 15 meters. Find the speed of the object when it is at a height of 15 meters. He wants the speed when it is here, 15 meters above the ground. We use W net equals to delta K, equals to K final minus K initial, which equals to half mv final squared minus mv initial squared. Right. What is the only force doing work? It's the weight, mg. What is the distance moved? 15 meters, because he wants it at a height of 15 meters. Cosine 180, because displacement upwards, mg is downwards, equals to all that. V final I want it, and V initial is 20, and you square it. If you calculate it, you get V final equals to 175 meters under the square root, meters per second. You see, it's in one line. You get everything in one line. You don't have to define an origin. You don't have to define a positive direction. You don't have to do any of this. If you like, even in the exam, you can use this. Nobody sees how you do the question, and nobody asks you to do the question in any given way. It's up to you how you want to do it. 3, find the speed of the object. Find the speed of the object just before hitting the ground. Yani, you see, what does the object do? It starts from here with a 20 meters per second. It goes up. As it goes up, its velocity decreases until it gets to 0. And then it starts moving down. Its velocity increases in magnitude until you get here, just before hitting the ground. What is the speed of that object? Okay. Now tell me, when it has gone from this point, gone up and come back down again, it's on the same line, by the way. What is the displacement when it comes back to this point? It's gone up.
0.
Yes,
Zero.
the displacement is 0. Ahsantu. The displacement is 0, and therefore W net equals to what? 0. As simple as that. Okay. So we say 0 equals to delta K, and the only thing is that V final equals to what? V initial. So the magnitude of V final must be equal to the magnitude of what? Of V initial, which equals to 20 meters per second. So as you can see, all the questions that we did can be solved using this formula, except one time. If he asks for time, we cannot use it because it does not have time. Okay. Now, in the earlier section, section 5, they asked me about the sign. Now I've asked for the speed, so I've taken the absolute magnitude. And the sign depends on whether you take upwards as positive or downwards as positive. If you take upwards as positive, this means V final equals to minus V initial, which equals to minus 20. And if you take downwards as positive, V final equals to plus 20. It depends on your direction. But the question did not ask for velocity. It asked for what? It asked for speed. So this is a golden opportunity for you. If you are not quite sure about equations of motion and how to use them, you can use this. Let's have another example and see how beautiful this formula is. What can we use it for? This is taken straight out of your book, Work to Stop a Car, which is how much work is required to stop a moving car. A car traveling 60 kilometers per hour, يعني كأن سيارة ماشية على 60 كيلومتر في الساعة, can brake to a stop in a distance of d of 20 meters. يعني this car, which is moving at 60 meters per kilometers per hour, when you apply the brakes, it can stop in a distance of 20 meters. We call this the stopping distance. Stopping distance, which is how long do you need to stop the car. It's called stopping distance. It's called the stopping distance. And here they refer to it as D, stopping distance, this one. This is the stopping distance, 20 meters. Now, if the car is going twice as fast, yani suppose now you are moving in your car at 120 kilometers per hour, which means the velocity is doubled. Tamam? What is the stopping distance? What would you expect the stopping distance to be? When it was 60 kilometers per hour, the stopping distance was 20. What do you think would be the stopping distance when we move at 120 kilometers per hour?
أكثر من 24.
هي أكثر من 20 مظبوط. But how much do you think? يعني I guess, I know we need to calculate it. Some people might think it is 2 times 20 is 40. Why 2? Because they think that we multiply the velocity by 2, it's 120. So multiply the stopping distance by 2 to get what? 40. And in fact, the answer no. We will see why. Okay? A lot of people will think the distance doubled, but no, it's not doubled. It's multiplied by 4, and we will see why. Now look at the car. It's moving with an initial velocity v1, which I like to call v initial, and eventually it has a velocity of v2 equals to 0, which I like to call v final. I always like to use initial and final. Now the car stops after covering a distance d. If you take the magnitude, this is displacement. So it stops after making a displacement of magnitude d in the positive x direction. Now, definitely this force, this braking force, must act where? Backwards, in order to stop the car. It does negative work, so the final kinetic energy is less than the initial kinetic energy. Use the word kinetic energy theorem, which is W net equals to delta K. In the book, he calls it delta KE. I like it to call it delta K. It's easier to use. W net equals to the magnitude of the force multiplied by the magnitude of the displacement multiplied by cosine 180. Cosine 180 is minus 1. So you get the net force done by the net work done by this force is minus F times D. What should this network be equal to? It should be equal to delta K, which is the exchange in kinetic energy. So minus F times D will be equal to half mv final squared, which is 0 because the car has stopped, minus half mv initial squared. He called it v1 squared, I call it v initial squared. It makes no difference. Now, if you use this formula, the minuses cancel out, and you can see very simply that F times D equals to half mv initial squared, which is the force times the stopping distance, which gives the work, equals to the initial kinetic energy, and therefore D, which I want, equals to m divided by 2f into v initial squared. Therefore, D, if you take m and f to be constant, D is proportional to what? The initial velocity squared. The stopping distance is not related to v initial, it's related to what? To v initial squared. Yani it depends on the square of the initial velocity. What does this mean? When the speed was 60, the stopping distance was what? Was 20. Right. What happens when we double the speed? Yani in other words, when v initial prime equals to 2v initial, what is d prime? شو يعني d prime؟ اللي هي new stopping distance. New stopping distance. نحسبها. It's simple. Look at this. D prime using this formula is going to be m over 2f into the velocity squared. But the velocity, the new velocity is 2 times the old velocity مش هيك؟ يعني هيا v initial equals v initial prime equals to 2v initial. So I evaluated here instead of v initial prime, what did I evaluate? 2v initial all squared. So this should be equal to 4 into m over 2f into v initial squared. لكن هاي m over 2f v initial squared هي what does it equal to? D. So you evaluate D, so you get D prime equals to what? 4D. So if you double your speed, what happens to the stopping distance? It's multiplied by what? By 4. We say the stopping distance is quadrupled. طيب, if we triple the speed, يعني we have 3V initial, what is the new stopping distance?
صار 9.
9 أحسن نعم. So at V initial 60, D equals to 20. At 100, at V initial equals to 120 kilometer, D prime new stopping distance شو بتساوي 4D بتساوي 4 times 20 شو بتساوي هنا 80. This shows us that when you double your speed, the stopping distance what? Doubles. That's why when you drive your car, you must leave a safe distance between you and the car in front of you. لازم نترك مسافة أمان ما بيننا وما بين السيارة اللي أمامنا. And the higher your speed is, the larger that distance becomes. Okay? Any questions on this? Okay. Let's deal with another type of energy called potential energy. Okay? Potential energy يعني طاقة الوضع. There are more than one type of potential energy. There is gravitational potential energy, which is potential energy due to the force of gravity. There is elastic potential energy, طاقة الوضع المرونية, due to a spring, يعني زنبرك. When you pull a spring, you store energy and it's called elastic potential energy. There is another type of potential energy called electric potential energy, and so on. You will only be asked for what? For gravitational potential energy, only gravitational potential energy. Okay, how do we define it and what does it mean? Look at this example. If we have a mass m, we have a mass m here, okay, this is mass m, it's above the ground at a height h. Now if you release this mass, شو يعني release it? يعني نتركها. ودائما كلمة release means dropping from rest. What happens to this mass? In which direction does it move? في أي اتجاه تتحرك؟
Downwards.
Yes, it will move downwards. Towards what? Towards the ground. Okay. So if you release this mass, it moves where? Downwards. This means that it had energy. That energy was stored in the system made up of this mass and the ground. We call it gravitational potential energy. Since the mass above this ground level, it moves towards the ground. We call this gravitational potential energy. طيب, how do we calculate the gravitational potential energy? It is simply, we define it or we give it the symbol U, okay, equals the weight, mg, the weight of that object multiplied by its height from the ground. Now, since the object here is above the ground, h is positive, so mg times h, and therefore the potential energy is what of this object is positive. With respect to what? This is the potential energy of this mass m with respect to the ground. It is positive. Okay, why? Because this h is positive because m is above this axis, the axis of the ground or the level of the ground. So whenever you talk about gravitational potential energy, you should say or you should state with respect to which surface you are talking about. يعني لازم تعطي مين؟ لازم تعطي surface. Okay. Let's take this simple example. We have, let's suppose this is the room where you are in. هاي الغرفة اللي أنت فيها. We have 3 levels and you have a room here, a table here. You have the level of the floor, مستوى الأرض في الغرفة. You have the level of the table here and you have the level of the ceiling. I call them S1, S0 and S2. S1 is the floor, S0 is the surface of the table, and S2 is the ceiling. Okay, S2 is the ceiling. Now, I want to calculate the potential energy of this mass M with respect to each level. Let's simply take this level, 0, هذا level S0. M is on the table, which means it's on this surface S0. What is the height of M above this table? What is the height of M with respect to this table? 0. It's on the table. So U0 will be equal to M times G times what? Times H. M times G times H, which equals to M times G times 0 and equals to what? To 0. So the potential energy of this object with respect to this surface is 0. You see, it's resting on this surface. طيب. What about the potential energy of this mass M with respect to the ground, the floor of the room? Now, if this table is not here, if you remove it and you don't hold this object, يعني ما بتمسكه, it will go where? It will fall down. Okay. Now, what is the potential energy of this mass M with respect to the floor of the room, يعني with respect to surface S1? It is going to be equal to the mass times the gravitational acceleration, which gives the weights, multiplied by the height of this mass above this surface. Now, M is above this surface. You can think of this as the x-axis, and the and H above the x-axis is positive, so it's mg times H1. So it possesses positive energy. What is the evidence for this? If you release an object here from rest of mass M, it falls down. So it has positive gravitational potential energy. Like, what about this level? If you have mass M here and you leave it, you release it, where does it move? Downwards or upwards? You just release it to تتركها, it will move downwards. Like, what do you need to move this mass M to this level, which is above it? You need an external force to move it, yes. So since this mass M is below this surface, it's below the surface, H here is negative, and therefore the potential energy of this mass with respect to S1, with respect to S2 is negative. Here it is, minus mgh2. So the potential energy of mass M relative to S2, negative U2, means work must be done to raise M to S2. We have to do work to take it up here. But if you release it, it will go down. You don't need to do work for it to go down. So it has positive energy with respect to this surface, but it has negative energy with respect to this surface. What I want to get at is the following. Whenever you define potential energy, you must tell me with respect to which surface you are defining this energy. يعني طاقة الوضع الناشئة عن الجاذبية الأرضية تعتمد على مين؟ تعتمد على السطح اللي أنت بتاخده كمرجع. We will see this in a lot more questions in the future. Let me ask you this question. Find the work done by the weight mg while an object is moved from surface S initial to S final. Yani we have two surfaces. This is the surface S initial, and this is the surface S final. Initial surface or initial level, and this is the final level. We have Y initial here, which is the position of level initial, and Y final is the position of the final level. And remember, Y initial and Y final are position vectors. They always start from the origin. So if you like, because I was asked about this morning, if this is my origin, Y initial is a vector that starts from here and goes up to this point. Y final is a vector that starts from here and goes up to this point. So this is the displacement made, which is y final minus y initial. Okay, displacement always delta y or delta x, so it's y final minus y initial. What is the work done by the force of gravity while this mass is moved from this level to this level? Note, in order to move it from the lower level to the higher level, we need a force to act. I called it F external, an external force, which is, maybe you do that force. Someone has to do this force. Maybe a rope or a wire does that force. Maybe a machine does that force. Whatever it is, you must have a force moving it where? Moving it upwards. So let me calculate that work by mg. I'm calculating the work by mg. So Wmg equals to the force mg multiplied by the magnitude of the displacement, which is d, multiplied by cosine 180. Why cosine 180? Because the force is downwards and the displacement is where? Upwards. This is displacement and this is force. So you get mg, and d is y final minus y initial multiplied by minus 1, which is cosine 180. Okay, so you get minus from here. Take mg into the brackets, you get mg y final minus mg y initial. So it's minus y final minus y initial. Always, whenever you have final minus initial, we call it what? Delta. Change in what? Change in potential energy. So it is delta U. So always, in all circumstances, the work done by the force of gravity equals to minus the change of the gravitational potential energy. Work done by the gravitational force equals to minus the change of the gravitational potential energy. Okay. Now, maybe you like to ask about what work is done by the external force. What does the external force do in terms of work? Let's take a simple case where this mass is taken upwards at constant velocity. Tell me, what does constant velocity mean to you?
Resultant force equals 0.
Exactly, resultant force equals to 0, and the acceleration therefore is 0. So what is the magnitude of F external, since the resultant force is 0? It
Equals
must be
mg.
mg.
So, yes, it equals to mg. So we have F external equals to mg, and therefore the work done by the external force is the magnitude of the force F external, which we agreed to be mg, multiplied by the magnitude of the distance, multiplied by cosine 0. Why cosine 0? Because F external is upwards and the displacement is upwards, so the angle between them is 0. So we get mg times d, which equals to mg. We agreed that before, that d is y final minus y initial. Take mg into the bracket, you get mgy final, which is u final, minus mgy initial, which is u initial. All this equals to what? Delta u. So the work of the external force equals to delta u, while the work of the weight was what? Minus delta u. Type, what is the net work done on the object? It is the work of all the forces acting on it, which is Wmg plus W external, and that is going to be equal to what? To 0, which is logical. We said that the object is moving up at constant velocity or constant speed because it's moving in a straight line. Okay, but this means that the velocity, the speed does not change, so the total work on it is logically to be what? To be 0, since it's moving upwards at what? At constant speed. Okay. Now we
دكتور
come.
بصير سؤال.
Yes.
هسا لما أحرك الجسم للأعلى بتزيد طاقة الوضع.
نعم.
مش المفروض كل زيادة في طاقة الوضع يقابلها نقصان في الطاقة الحركية؟
هذا in free fall. هذا in free fall صحيح. يعني you is this free fall؟ هذا
No.
free fall. مش free fall هذا. فلو كان free fall يعني لو كان جسم if you have an object moving upwards only under gravity which is free fall as it moves up potential energy increases and kinetic energy what decreases. صحيح. We will come to this. هذا بيسموه حفظ الطاقة الميكانيكية conservation of total mechanical energy. But هون over here تمام you have another force acting. مظبوط. ف you don't get the increase in that equals to the decrease in the other. We will come to
تمام
this.
وصلة.
Yes, we will come to this. We will do it in detail. This is a good question. Okay, let's see what we mean now by conservative and non-conservative forces. A conservative force means بترجموها بالعربي قوة محافظة. هذا معنى conservative force. يعني if you translate it to Arabic. And non-conservative forces يعني القوة غير المحافظة. هاي يعني قوة محافظة وقوة غير محافظة. Okay. How do we define a conservative force? A conservative force has the following two properties. يعني إلها خاصيتين التاليتين. الخاصية الأولى or the first property is that the work of a conservative force. طبعا المقصود فيه the work done by a conservative force. خليني the work done by يعني or the work of a conservative force or if you like you can write it as the work done by, if you like. The work done by a conservative force does not depend on the path. يعني شغل القوة المحافظة لا يعتمد على المسار اللي بيتحرك فيه الجسم. The work done by a conservative force does not depend on the path. And the other one, the work of a conservative force round a closed path is zero. يعني شغل القوة المحافظة حول مسار مغلق يساوي صفر. We will see exactly what each one means. Now, we will do an example to prove each one and to really understand what we mean by the first one and what we mean by the second. Let's take the first property, which is the work done by a conservative force does not depend on what? Does not depend on the path. Okay? يعني لا يعتمد على مين؟ على المسار. Let's see what this means. Which is the conservative force that we are dealing with now? It is the force of gravity, which is the weights. And as you can see, I have an inclined plane from A to C, and I have completed this to form a right angle triangle. Now I want to ask the following. What is the work done by the weights, which is the force of gravity, in moving this mass M from point A to point C? So my first path, أو مساري الأول, is moving M from where to where? From A to C. And of course, there is a force that is acting to move it. But I'm not drawing this force because I am interested in the work of gravity only. So my first path is to go from A to C directly. هذا مساري الأول. And then I want to choose another path. أعطوني مسار ثاني ممكن أوصل فيه من A إلى C. Give me another path where I can go from A to C. A simple one.
من A ل B بعدين من B ل C.
أحسن. Now I can go from A to B and then from B to C. So how many paths do I have now? I have from A to C directly, this is my first path. And then from A to B to C, this is my second path. Now, the first property says that the work done by the weight by going from A to C through this path must be equal to the work done by the weight in going from A to B and then from B to C. هذا معنى إنه the work done by a conservative force does not depend on the path taken. Let us prove this. Let us prove it. Look at this. I have, I'm going to go from A to C directly. Now the weight, as you all know, can be resolved into two components. One which is parallel to the inclined plane down the plane, and the other is perpendicular to the inclined plane. Now this is the length of the inclined plane, D. And since I am going from A to C, then the displacement is up the plane like this. This is the displacement. Okay. Now, if I ask you, while this mass is moved from A to C, which component of the weight, mg sine theta or mg cosine theta, does work? Which one of those two do work?
Sine theta.
نعم. طب ليش this one does no work؟ ليش؟
زاوية
لأنها
الإزاحة.
أيوة عمودية على اتجاه الإزاحة هاي. وعشان هاي تعمل شغل بده يكون إزاحة على هذا الاتجاه، وما فيش إزاحة على هذا الاتجاه as I heard one of you said. And we are interested in this movement, this force, or this magnet, this force is perpendicular to this displacement, so it does no work. This is the only component that does work. So what is the work of this force? Now the magnitude of the force is mg sine theta. Here is mg sine theta multiplied by the magnitude of the displacement. Here it is d. Now what is the angle between this force and d? This is down the incline. This is up the incline. What is the angle between them? It's 180 degrees. Therefore, the work done by the force of gravity when the object moves from point A to point C along the inclined plane is minus mg d sine theta. But remember, this is a right angle triangle. This is the horizontal component of the displacement. This is the vertical component of the displacement, which I called it h. Now h is opposite to theta, so it takes sine or cosine. It takes sine. I am resolving this displacement into two, one along this axis, horizontal axis, and one along the vertical axis. Since this component, which is I called h, is opposite to theta, it takes the sine, so it is d sine theta. This is the vector that we are analyzing. We made it the hypotenuse, يعني الوتر of a right angle triangle. This is opposite, it takes the sine, so h equals to d sine theta, and immediately I get that the work done by the force of gravity, which is the weight, and when the object moves from A to C is minus mg times h, and h instead of d sine theta. So this is the work done by the force of gravity when I move from A to C directly. Now let us try the other path, which is from A to B, and then from where? From B to C. Now this work of mg from A to B to C is wmg from A to B plus wmg from B to C. Okay, from A to B, and then from B to C. Type from A to B. Okay, when the mass m is moving along this direction, I have called the displacement to be d1, and its magnitude is d cosine theta. But note that the displacement is to the right, while the force is vertically downwards. mg now vertically downwards. What is the angle between them? 90. So what is the work of the force of gravity when the object moves from A to C?
0.
0. بالضبط. That's 0. Now we go to the other section of the path, of the second path, which is from B to what? To C. So the work done from B to C equals to mg, which is the weight downwards, multiplied by how much distance it moved upwards, which is h, multiplied by cosine 180. Why cosine 180? Because the displacement is upwards while the force is downwards. So they have a 180 degrees between them. So you get the work done from B to C is minus mg times h. So what is the total work from A to B to C? We say it is from A to B, which is 0, as I have written above there, plus from B to C, which is minus mgh. So if you add them up, you get the work done in going from A to B to C is really minus mgh, as before when we went from A to C directly, it was also minus mpg for h. So the question is, does the work done by the weight, which is the force of gravity, depend on the path. We've taken this path and we have taken another path. Does it depend on it? No. In both cases, the same work was done. This is the property of a conservative force. Even if you go along this path, like this, the same amount of work will be done. Even if you go like this, the same amount of work will be done. Why? Because the force of gravity is a conservative force. So we have proved property number 1, which is the work done by the force of gravity does not depend on the path. Now let us prove the other one, the next one, which is find the work done by gravity when the object moves from A to B to C back to A. لاحظوا, from A to B to C back to A. We call this a closed path. We call this a closed path. يعني مسار شو ماله؟ مغلق. We call this a closed path. From A to B to C back to A. هذا شو بنسميه؟ مسار مغلق. Now, according to the second property, this work must be equal to what? To 0. If the force of gravity is a conservative force, which it is a conservative force. Let us prove this. I want the work done by gravity in moving from A to B to C back to A. Tamam? This is going to be equal to Wmg from A to B to C, which I calculated before and was minus mgh, plus the work done from C back to what? Back to A. Now let us calculate this from C to A. Okay, there, from C to A. Now from C to A, and the displacement is where? Is downwards. And the component that does the work is also downwards. So the angle between them is 0, and cosine 0 equals to what? To 1. So we have mg sine theta multiplied by d multiplied by cosine 0, which equals to mg d sine theta. But we know from before that d sine theta is called what? It's called h. So it is mgh. So the work done from A to B to C is minus mgh, and you add to it the work done from C to A, which is plus mgh. It gives what? It gives 0. So yes, when you start from a point and you go back to the same point, the work done by the force of gravity, which is a conservative force, is what? Is 0. So does the work of gravity around a closed path equal to 0? The answer is yes. Now I've taken a simple path just to be able to calculate the work. Suppose someone did the following. He started from this point here, point A, and he moved along this direction, along this path. Okay, along this path. And he's gone back to point A. What is the work done here by the force of gravity?
0.
0. Why? Because it is a closed path. Yani, let me put it this way. The work of gravity only depends on the initial position and the final position. That's all it depends on. Okay? The force of gravity does work only when an object moves in a vertical direction. If you move 1 million miles along a horizontal direction, the force of gravity does 0 work. يعني مهما تحركت على المحور الأفقي إن شاء الله بتتحرك مليون كيلو، الفورس of gravity does 0 work. ليش؟ لأنها عمودية على اتجاه الإزاحة. When does gravity do work? When the elevation، يعني لما الارتفاع تبعها شو ماله؟ يتغير. فthose are the two properties of what? Of a conservative force. The work does not depend on the path. This is the first one. And the second one, the work around a closed loop equals to what? To 0. Any questions on this? Okay. Now in section 5,